the beam problem. So I'll continue the problem number. So this is my fifth problem. So I have a cantilever beam now. See, in beam I have cantilever beam, I have simply supported beam, and I have fixed beam. Okay, so these are the problems you are going to solve under beam. So let us start with cantilever. Once again, under cantilever, I have point force, I have UDL, and I have UVL. Okay, similarly, simply supported beam, point force, UDL, UVL, similarly fixed beam. Okay, so we'll continue with the cantilever beam with point force. That is my fifth problem. So fifth problem is my cantilever beam with point load at the free end. Okay, so using RR method, I need to find out. Now here I will use the word deflection because beams are subjected to transverse load, and because of this transverse load, uh, it is having the deflection in vertical direction. Okay, so this is my cantilever beam subjected to a point force P at the free end and having a length L, and it is having an Young's modulus E. Now please remember, beams comes with moment of inertia I, not area. Bar comes with area, whereas beams comes with moment of inertia, because many times I have seen student writing equation for beam with E and A. So that is a mistake we are doing. So please remember, beam comes with Young's modulus and moment of inertia, that is I, whereas bar comes with Young's modulus and area. Okay. Now once again, the first step, here same RR method I have to use, and here I need to find out what is the deflection. What is the deflection at the free end? So what is the deflection in case of a cantilever beam subjected to point force? Because in a design you have used all beams with deflections, no, maximum deflection. So in a cantilever beam, if you use or if you refer any of the design data and book, the deflection Y, maximum deflection Y max. So that is what we are going to consider. My maximum deflection Y max in case of a cantilever beam subjected to point force at the free end is given by PL cube divided by 3EI. This equation, standard equation, which is there in any of the design data and book. Similarly, cantilever beam with UDL, the Ymax is different. Then cantilever beam with UVL, Ymax is different. So all those Ymax values are given in design data and book. Please go through that values, and let me go with RR method, and we'll check whether we'll get the same equation or not. So same thing, five steps are RR method, same 5 steps. Formulate, what is first step? Formulate the P function. So to formulate the P function, what is required? I need a strain energy plus work potential. These two things are required. Now strain energy in case of beam is different. Now I cannot use this equation. See, I cannot use this equation. This equation I cannot use as a strain energy, because this is the equation for bar. When I come for the beam, the strain energy equation changes. So that you have to obtain. So my strain energy will be equal to integration over the length of the beam. See, this is the equation we have derived in mechanics of metal. It is m square divided by 2EI. This is the what my strain energy equation. But I need to represent this m in terms of partial differential equation. So this m I have to substitute in terms of partial differential equation. So for that, what I need to have differential equation, what I need to do, then to substitute that, I'll use the relation. That is what we call it as a equation of deflection. So what is my, how your bending equation, torsion equation, like that I have a deflection equation. So which is given by 1 divided by R is equal to, it is m divided by EI. See, once again, this equation you will get it in any of the mechanics of metal book. So 1 divided by R is equal to m divided by EI. That will be equal to d square V or d square Y divided by dx square. So this is what we have, deflection equation. This is what we call it as deflection equation, or it is sometimes also called differential equation of deflection. This equation we call it as, simply call it as deflection equation or differential equation of deflection. Okay. Now using these two relation, I'll get the value of m. Therefore, my m is equal to, it is ei into d square y divided by dx square. Okay. So as I told, in FEM, x will be represented as u, y will be represented as v, and z will be represented as w. So now instead of y here, let us consider it as a v. Therefore, it is ei d square v divided by dx square. No problem. If you keep y also, there is no problem. But in FEM, these are the notations we are following for x, y, z. So instead of y, I'll consider it as a v. Now I'll substitute this value of m in this strain energy equation. So what I am going to get? So my strain energy will be equal to integration 0 to L. Now I'll apply that limit 0 to L. So m square. What is m square? M is ei into d square v divided by dx square whole square. Why whole square? Because m square is there. This is my entire term m. I'll square it, divided by 2ei as it is. This 2ei, I have kept it as it is. Now further I'll do the simplification by applying this square to both the terms here, because it is ei into d square v divided by dx square is there. Therefore, what I am going to get strain energy? My strain energy will be equal to integration 0 to L. It is ei square into d square v divided by dx square whole square whole divided by 2ei. So here 1 ei will be get cancelled. 1 ei is left out. So that 1 ei and this 2 I'll take it outside the integration, which is constant. So my strain energy will be equal to, it is ei divided by 2 integration 0 to L. It is a d square v divided by dx square. Of course, I have with respect to dx here, integration is there, means that will be with respect to dx. Therefore, that dx will be as it is. So this is d square v divided by dx square whole square into dx. So this is my strain energy equation. Now once again, this strain energy equation is fixed for any type of beam, whether it may be cantilever beam, simply supported beam, or fixed beam, or propped cantilever beam. You consider any type of beam, this strain energy equation is fixed. Now instead of directly writing this, once again I have derived how you obtain this final equation. Now in the examination, what you can do is you can directly write this strain energy equation. We know that the strain energy is given by this equation. Okay. Now strain energy equation we obtained. Now I have to get the work potential. So what is work potential? It is force into deflection now. So let us consider V1 is the deflection which is there at the free end. And work potential is negative. So I'll put that a negative sign. So this is my equation number 2 and this is my equation number 3. And this PE function is what my equation number 1. Now what I need to do, I need to substitute this strain energy and work potential into PE function. So my PE function pi will be equal to, it is ei divided by 2 integration 0 to L d square v divided by dx square whole square into dx minus p into v1. So this is my PE function. Now first step is over. I have formulated the PE function. So this is my entire PE function. Now I'll go to the second step. What is second step? You have to assume trial displacement function. You have to assume a trial displacement function. Now, as I am using the word trial, see, I don't know initially whether I have to consider up to second order or third order or only first order. If you are considering up to second order, and if you are not getting this equation, then you have to increase one more term. So I have done for, initially I have done for second order and I have not got this equation. You can try that also. I am not getting this equation if I consider up to second order. So if I consider third order polynomial function, I am going to get the exact equation. Therefore, now I'll consider a polynomial function up to third order. And now the deflection is in y direction, therefore I'll take it as v instead of u, because bar is having an extension in x direction, or deflection or displacement in x direction. Therefore we are going to consider that displacement as u. But here the displacement or deflection is there in y direction, therefore we are considering it as v. And instead of a0, a1, a2, let us consider another polynomial with another constant, that is b0 plus b1x plus b2x square plus b3x cube. Okay, so this is the third order polynomial function I am going to consider. Now once again, the assumed displacement function should satisfy the given boundary condition. So I have to put those boundary conditions here. So what is same boundary condition? When x is equal to 0, what is my v? What is my v? So in this beam, here is what my x is equal to 0, and here I have x is equal to L. So when x is equal to 0, my displacement is 0 because it is fixed end. Therefore, substituting v is equal to 0 and wherever x has 0. So what I am going to get? 0 is equal to, it is b0 plus b1 into 0 plus b2 into 0 plus b3 into 0, because all these three terms are consisting of x, and wherever x I need to put it as 0. Therefore, what I am going to get? I will get b0 is equal to 0. So one constant I will get it by considering the first boundary condition. Similarly, I'll go with the second boundary condition, that is x is equal to L. When x is equal to L, I have v is equal to v1, or you can also call it as vmax. So I'll be having maximum deflection, because when point force is applied like this, so this is the beam which is going to deflect like this. So this is the beam which is going to deflect like this. That means this is the maximum deflection which is there at the free end, and this deflection is goes on reducing when you move towards the fixed end. So this is what we call it as an Ymax in case of mechanics of material, and here we are call it as Vmax, okay, or V1. So that is what I am going to consider it as an V1 or Vmax. So let us put wherever v as V1 and wherever x as L in the displacement function. So I'll get V1 is equal to, in the previous step I obtained the value for B0 is 0. I'll eliminate that. Then I have B1 into x, x is now replaces with L, plus B2 into L square plus B3 into L cube. So this is the B1 expression. So there once again I need to get the value of B1, B2, B3, so that I will get the value of V1. But I have one more boundary condition. Using that boundary condition, I can eliminate another constant also. What is that boundary condition? When x is equal to 0, my slope is 0. Correct, no? In cantilever beam, I don't have any slope here, whereas I have a slope at the free end. So this is the slope which is I have at the free end. Whereas in the fixed end, I don't have any slope. Therefore, when x is equal to 0, my slope is 0. That is dv by dx is equal to 0. Slope is nothing but differentiating that particular deflection with respect to x. I am going to get the slope. So this is the dv by dx is equal to 0. So what you can do is you can differentiate this v with respect to x and equate it to 0. Anyhow, now my b0 is 0. Only these remaining terms I'll differentiate. So what I'll do, dv by dx is equal to what is that? b0 is 0. I have b1 into x. X is 1 plus 2 b2 x plus 3 b3 x square. If I differentiate that v with respect to x, this is the equation I am going to get, and you equate it to 0. Because after differentiating, that slope is equated to 0, so I'll equate it to 0. Now, wherever x, that x should be replaced with 0. Therefore, this term I'll get 0. And when I put 0 here also, so this term is 0. Therefore, I'll get b1 is equal to 0. So this is another constant. I am getting by considering another boundary condition which I have not done in bar problem. So please remember, this is another boundary condition I have to consider to make another constant. Otherwise, what happens if you don't consider this boundary condition? Three unknowns means you will get three simultaneous equations. So it becomes very tedious to solve manually the three simultaneous equations. So by considering anyhow, I have an option of considering the another boundary condition, so that there I am going to get B1 as 0. Now therefore my B1 equation reduces, as this B1 is 0, 0 into multiplied by L, it will become 0. Therefore my B1 equation is B2 into L square plus B3 into L cube. So this is my final B1 equation. Once again, in this equation I have to find out B2 and B3. So once if I get the value of B2 and B3, I can able to get the value of V1, which is equal to PL cube divided by 3EI. We'll check that. And similarly, at any random distance, when x is equal to x, V is equal to V. Therefore, my V is equal to, see, B0 is 0, B1 is 0. So first two terms you can eliminate. Remaining is B2 into x square plus B3 into uh, B2 into x square plus B3 into x cube. So this is the equation for any random distance. So these are the two important equations to get the value of displacement, which is at the free end. This is the expression to get the deflection at free end, and this is the equation to get the deflection at the at any random distance. Now I'll come to the P function. What is my P function? Pi is equal to, it is EI divided by 2. See what my second step says. Once it satisfies the boundary condition, I have to substitute the displacement function into P function. So let me write the P function first. It is EI divided by 2 integration 0 to L d square V divided by dx square whole square into dx minus P into V1. So this is my P function. Now here I have to differentiate this V twice, and whatever the value I am getting, that I have to square it. Now instead of substituting this V here, let me do it separately. First I will differentiate dV by dx. I mean I will differentiate V once. You already done. Where here you already done. What I have obtained? I have obtained B1 plus 2B2x plus 3B3x square. So that I'll write down. When I differentiate V once, I'll get B1 plus 2B2x plus 3B3x square. But in the equation, it requires 2 times. Therefore, I'll differentiate it once again. That V, I'll differentiate it once again. So B1 is constant 0. It is 2B2 plus 6B3x. X square is 2x. 2 into 3, it is 6. So B3 as it is. So this is 2 times differentiation of V. Now this value I have to substitute here and I have to square it. And you know the value of V1, that V1 I'll substitute. Therefore, my pi is equal to, it is EI divided by 2 integration 0 to L. What is the value of d square V divided by dx square? It is 2B2 plus 6B3x whole square into dx minus P into what is B1? B1 is 2B2L plus I mean B2L square. Here I have V1 here, which is B2 into L square plus B3 into L cube. So B2 into L square plus B3 into L cube. That I am substituting. Then next step is only I need to do the simplification same way how we are done previously. This I have to expand with A plus B whole square. Then I'll take this P inside the bracket. So that simplification I am doing here. So it is EI divided by 2 integration 0 to L. It is 4B2 square. I mean A square plus B square plus 2AB. I am doing that. Directly I am writing the equation here. 2 square 4 B2 square as it is plus it is 36 B3 square x square plus 2A into B. This is 2 into a into b. This is the expansion of this term with a plus b whole square into dx as it is. Then let us take this p inside the bracket with negative sign. So it is p into b2 into L square minus p into b3 into L cube. Now in the next step, what I need to do, I need to integrate this. You integrate this with respect to x, then you can put the limit 0 to L. So pi is equal to, I have ei divided by 2 outside. So 4 b2 square x, integration of this constant is x, plus 36 b3 square, integration of x square is x cube by 3. Correct now? Integration of x square is x cube by 3 plus here 2 into 2 4 6 into 4 it is 24. Correct now? 6 into 4 is 24. b2 b3 as it is. b2 b3 as it is. Now integration of x is x square by 2. Then 0 to L. And this minus p b2 L square and minus p b3 L cube as it is. Now wherever x is there, you put the upper limit and minus lower limit. See, all this term, and this, all these three terms are consisting of x. Therefore, by substituting lower limit, entire term will become 0. Therefore, I'll substitute only the upper limit. Therefore, my pi is equal to ei divided by 2. What is my first term? 4 b2 square into L. 4 b2 square into L. X is now replacing with L, plus 36 b3 square. 36 b3 square into L cube by 3. Means here x is there. Now this x will replace us with L, plus 24 b2 b3 plus 24 b2 b3 L square by 2. Correct now? So here once again this x will be replaced us with L by 2 as it is. Minus lower limit is 0, that I leave it. Minus p into b2 into L square minus p into b3 into L cube. The term I'll keep it as it is. Now this is the simplified, or further if you want you can simplify it and you can minimize it, because here it is 2, this is 12, 3, this is 12. Okay, so pi is equal to, it is ei divided by 2 4 b2 square L plus 12 b3 square L cube plus 12 b2 b3 L square minus p b2 L square minus p b3 L cube. Okay, so this is now my simplified p function. Now I'll go with the fourth step, that is minimize p. You minimize the p function. Now once again, to minimize p function, which are the two constants? I have b2 and b3. Therefore, I have to differentiate this p function with respect to b2 first and equate it to 0. Similarly, the same p function I have to differentiate with respect to b3 and equate it to 0. So I'll get two equilibrium equations, solve those two equations to get the value of b2 and b3. Substitute these values of b2 and b3 in b1 equation. Okay, so I'll do that. First, I'll differentiate with respect to b2. Outside, I have constant ei divided by 2. That I'll keep it as it is. When I am doing with respect to b2, my b3 will become constant. When I am doing with respect to b3, b2 will become constant. So now I am doing with respect to b2. So b square, differentiation of b square is 2b2. Means 2 into 4, it is 8 b2l plus b3 is constant, therefore this term is 0. Here it is 2 b3 b2, differentiation of b2 is 1. Left out constant term is 12 b3 l square minus, when I am doing with respect to b2, this term will become 0. Left out is p into l square is equal to 0. differentiate and equate it to 0. This is my first equation. Similarly, the same P function I have to differentiate with respect to B3. When I'm doing with respect to B3, this B2 will become 0. This is first term is 0. Outside I have EI divided by 2 as it is. Then here B3 square is 2B3. So 12 into 2, it is 24. 24 B3 L cube plus 12 B2 L square minus, now this term is 0, minus P L cube is equal to 0. So further, I'll take this EI inside the bracket. So it is 2, this is 4. Therefore, what I am going to get? 4 EI L B2 or B2L, anything. Then it is 2 and here it is 6. So it is plus 6 EI, 6 EI L square B3. 6 EI L square B3 minus PL square as it is equal to 0. Similarly, this EI also take it inside. So it is 2, this is 12. So it is 12 EI L cube B3. Then this is 2, this is 12, 6. Means it is plus 6 EI, 6 EI. What is that? L square, 6 EI L square. Sorry, 6 EI L square B2 minus PL cube is equal to 0. Now, I need to solve these two equations as a simultaneous equation. But here, some of the terms I need to cancel here. Suppose if I want to cancel this, so what I need to do, if you multiply this first equation with 2L, now your purpose will be served. I'll tell you. So this equation I'll multiply with 2L. If I multiply with 2L, what I am going to get? It is 8L square EI B2 as it is. It is a 12 EI L cube by L cube into B3 minus P into, 2P L cube. So I'll write that. If I multiply with 2L, it is 8 EI B2 L square. 8 EI B2 L square. L into L, it will become L square. Plus 12 EI B3 L cube. 12 EI B3 L cube minus 2 P L cube is equal to 0. This is the equation I am going to get when I multiply this first equation by 2L. Second equation will keep it as it is, but only thing is while writing, I'll rearrange the terms. So this 12 EI L cube B3 I'll take it to the here. So 12 EI B3 L cube. Then second term is what? 6 EI B2 6 EI B2 L square. Then minus P L cube is equal to 0. Now you can solve this equation. Now you can solve this equation as a simultaneous equation. Their second term will be get cancelled. And further you can get the value of B2. So this is minus, this is minus, this is plus. So these two terms will be get cancelled. One is plus, another one is minus. Here 8 EI B2 L square minus 6 EI B2 L square, then minus 2 PL cube plus PL cube is equal to 0. From these two terms, you can take 2 EI B2 L square as a common, keep the remaining terms, and here send these two terms to the RHS. This is negative. When I send it to the RHS, it will become positive. Similarly, this is positive. When I send it to RHS, it will become negative, because these are the two terms which are not consisting of any EI and B2. Constant terms means this is the term which is not consisting of any unknown B2. So that I have taken to the RHS. After simplification, I got the value of B2 as PL divided by 2E. Then substituting this value of B2 in any one of equation here, you will get the value of B3, and that value of B3 is minus P divided by 6EI. I'll go with the final step, that is fifth one, finding the displacement. So I need to find the displacement, that is my V1. So V1 is equal to, what is the equation for V1? It is B2 into L square plus B3 into L cube. So this is what my value of V1. So now let us substitute the calculated value of B2 and B3. B2 is PL divided by 2EI into L square. So this L square I have kept it as it is, plus B3. B3 is minus P divided by 6EI into L cube. This L cube as it is. Further, I'll do the simplification. V1 is equal to, this is L into L square, it will become L cube. So it is P L cube divided by 2EI. Then plus into minus, it is minus P into L cube, it is PL cube divided by 6EI. Okay. So this is what the simplification. Further, if I do the simplification, what I will do here, I will take PL cube divided by 2EI common. So it is PL cube divided by 2EI. I'll take it common from these two terms. Then here it is 1 minus 1 by 3. Right? So 1 minus 1 by 3, because PL cube EI already taken outside. Then can you tell me 1 minus 1 by 3, what is the value? 2 by 3. Okay. So it is 2 PL cube divided by 6, because 2 by 3, no, 2 by 3, 3 into 2, it is 6. Yeah. Now this is 2, this is 3. Therefore, it is PL cube divided by 3EI. So this is the final equation. So as I told, when I begin the problem, here I have mentioned here, see, according to mechanics of material, my maximum deflection, this is my maximum deflection which is there at the free end, and that value is PL cube divided by 3EI. So this equation is there in any of the design pattern book if you check it, or any mechanics of material book if you check it. In case of a cantilever beam subjected to point load at the free end, this is the maximum deflection. So same equation I have obtained here by using RR method. So this is PL cube divided by 3EI. Okay, now after this I need to find out the displacement at any random distance. So that is nothing but my V. V is nothing but B2 into X square plus B3 into X cube. So this is value of V. I will show it once again here. This is my value of V, which is at any random distance. So V is equal to B2 into X square plus B3 into X cube. So same thing I written here, B2 into X square plus B3 into X cube. Therefore, let us substitute once again the value of B2 and B3. B2 is PL divided by 2EI into X square plus B3 is minus P divided by 6EI into X cube. Okay. So further simplification, what I am going to get here once again, what you can take, P divided by 2EI common. So my V is equal to P divided by 2EI. If I take it common, what is left out? L into X square is left out. Plus into minus, it is minus. P divided by 2EI you are taken. So it is X cube divided by 3. So this is the equation which is at any random distance, where if I substitute X is equal to L by 2, I'll get the displacement at the center of the beam. Similarly, if I put X is equal to L, definitely I am going to get the same equation of PL cube divided by 3A. Okay, so this is something like a general equation where by substituting the value of X, you will get the displacement at that particular distance. Okay guys, we will continue with some more problems on beam using RR method. Thank you for watching. Please like, comment, share and subscribe the channel.